Okay, so is there any pattern here?
There's no pattern here.
No pattern, है ना? It is just like the somebody is spreading some salt on paratha.
Now we are going to see the attraction of magnets.
Keep at some critical distance. Okay, it is okay. So everyone has come to know that these are opposite poles, है ना? These are opposite poles. You put one paper. Take this paper. Take this paper. Put over it. Sure. Okay. So now there are two magnets. Okay, with opposite poles facing each other. Okay, with opposite pole facing each other. Let us sprinkle now. Where do you think the magnetic field is strongest?
Here.
Center, huh?
Center.
Okay.
We saw there was one magnet and one magnetic field starting from one pole and ending on the other. But here we see there are two magnets but three magnetic fields. One starting here, ending here, one starting here and ending here. But the third one is in the middle, like this, as you can see. Because the magnetic field is the strongest in the middle, because two magnetic fields are colliding with themselves. So the force is the strongest in the middle of the two magnets.
Where the density is more, where the field is strong or weak?
Here it's strong.
Okay, wherever the density is more, their field is stronger.
Yeah. See, we have kept the repelling poles together and we have sprinkled some iron fillings on the paper. So these two are the repelling poles. Here you can see the magnet, but this time there is no third magnetic field at the center. This time each magnet has its own magnetic field, and more iron fillings are attracted to the poles and not in the center.
What is the case here?
Here the opposite poles are kept together and the magnets are attracting each other.
So magnetic field strength is
Very strong.
strong.
Yes.
With the concentration of filing, we can say that magnetic field strength is so strong. Huh?
Yes.
Okay. Here
Here the repelling poles are kept together, the same poles of the magnet. So there is very less attraction and very less iron fillings are found in the center.
so south and south. Huh?
Yes.
More magnetic field in the means here. So there are more iron fillings here. So here we have kept the like poles, so they are repelling. So here there is no magnetic force.
In the magnets, there is even 3D force. This is 2D force like this. It is even pulling like this. There are forces like this also, but we are not able to do a 3D experiment. As you can see, they are standing here. So because they are pulling like this also, the poles.
We are taking a ring magnet and 2 sheets of papers and some iron fillings. Now we have spread some iron fillings, and in the center it is rising slowly, and more magnets are attracted around the ring magnet. And what we don't know is that whether it is entering from here or coming out from there.
The shape is like it is coming from here and going down. From magnet, it is coming from here and going here. This is one pole and this is one pole.
So how do you say that here it is entering or leaving? Can you can you show some? Huh?
You can post.
Is it really standing?
Yes,
No.
little bit.
No, here it's.
Okay,
yeah,
so
here,
it is standing like as if it is small Mount Everest.
Can I post a bit?
Hmm?
Can I pour a bit? I am feeling.
It is really standing. Huh? Pour some more and finish. Is it standing?
Yes, uncle.
Uncle, it is straightened.
So these are vertical, huh?
Uncle, यहाँ पे stand हो रहा है.
हाँ, सब जगह हो रहा है.
Okay, so
और
it is
ऊपर वाला यहाँ के.
Uncle, can I support? हाँ, वही.
अब उठो.
उधर से.
Wow. It is really like donut, whatever you had drawn on the pole. है ना? Okay. Wow.
I've placed my hand. I've placed my hand also.
Good.
Uncle, see on the top.
हाँ. Acha, here there are no lines, na? No. It means the field is absent there.
Absent.
It is random distribution.
Oh.
Oh.
The video which you just saw, it had in there, it was just rotating, because when electricity passes, this copper coil becomes like a magnet. It acts like a magnet, and there's a magnet here. So when electricity passes, that time this also becomes a magnet, and it starts to rotate like this. The copper wire is rotating because when the electricity passes through the copper coil, then the copper coil acts like a magnet. So when it acts like a magnet, there is one more magnet fixed with the battery. So the copper wire rotates due to the two magnetic fields which are made. One is permanent magnet, one is temporary magnet, which is rotating. Temporary magnet is not fixed, so it is rotating, and the permanent magnet is fixed, so it can't rotate.
A current carrying wire creates a magnetic field around it.
A current carrying wire creates a magnetic field around it.
A current carrying wire creates a magnetic field.
A current carrying wire creates a magnetic field around it.
A current carrying wire creates a magnetic field around it.
A current carrying wire creates a magnetic field around it.
A current carrying wire creates magnetic field.
A current carrying wire makes magnetic field, and the more number of turns it has, it will have more magnetic.
Carrying wire creates magnetic field. A current carrying wire makes magnetic field.
Okay.
Here is the copper coil turned many times, and here is the magnet which is hanging freely by a thread. Here is the north direction and here is the east. The red pointer is showing east direction. There are so many turns of the coils here, because the more turns of coil is there, the more stronger the magnetic field will be. Suppose we are turning only once, then the current will pass only one time, but if we do 15 more times, then the magnetic field will increase 15 more times, and the current passing through the coil will be 15 more times. And since we have turned it so many times, it will give a strong magnetic force enough to push this magnet.